Good afternoon, student. In the previous class, we started our unit 3, that is image compression. And in previous class, we have studied fundamentals of image compression, and we have seen different types of redundancies. Let us revise the content of previous class quickly. So we have seen this example which illustrates the importance of compression. Then we have seen different terminologies. Definition of data compression, so which is the process of reducing the amount of data required to represent a given quantity of information. And then we have seen the difference between data and the information. So actually the data is the mean by which information is conveyed. Okay, so we have seen the same information can be represented using different amount of data. Then next we have seen different applications of image compression. Then we have seen the definition of compression ratio. So it is the ratio of number of bits required before compression to the number of bits required after compression. Then we have seen the definition of relative data redundancy, which is represented by R, and it is computed using this equation 1 minus 1 upon C. And what is the meaning of this R value? So if we have R equals to 0.9, that represents 90% of the data in the original data set was redundant. Okay, so that is the significance of this value. Then we have seen this tree diagram where we have shown different types of redundancy, and we are interested in these three types of redundancy. And any data compression model will try to reduce or eliminate any one or more of this redundancy. Then we have seen these three types of redundancy in detail with examples. Now let us summarize those redundancies. First one is the coding redundancy. So this redundancy happens when we use more number of bits than actually needed. Okay, so for gray images we generally use 8 bits. So 8-bit codes that are used to represent the intensity in most 2D intensity arrays contain more bits than are needed to represent the intensities. So if we use 8 bits to encode all the pixels, that scheme is known as fixed length coding. But we have seen if we use variable length coding, then we can greatly reduce this coding redundancy. Then second type of redundancy is known as interpixel redundancy or spatial and temporal redundancy. It is due to the spatial correlation between the neighboring pixels. So same information is unnecessarily replicated in the representation of correlated pixels. Then we have psychovisual redundancy, or also known as irrelevant information. This redundancy is due to the limitation of human vision system, because most 2D intensity array contain information that is ignored by the human visual system. We have seen the one example where this was the example. So this image is containing the intensity range from actually 125 to 131, but we are seeing only one gray level. Our human visual system is actually averaging those intensity range. Okay, so we are seeing only one gray level. This results in psychovisual redundancy. Now let us discuss general image compression model. An image compression system is composed of two functional components, which is known as encoder and decoder. The input image, which is represented by f of xy, is fed into the encoder, and after encoding we get the compressed data for storage and transmission. This decoder module performs the complementary task of the encoding. So it will reconstruct the image from this compressed data, and the compressed image is represented by this f cap of xy. If this reconstructed image, which is represented by f cap xy, equals to original image, that is f of xy, then that compression system is known as error-free, lossless, or information preserving system. Otherwise, if we get the distorted image after decompression, then that compression system is known as a lossy. Okay, I repeat, if this f cap xy equals to f of xy, then that compression system is known as error free, lossless, or information preserving system. If we get the distorted image, that means this f cap xy is not equals to f of xy, then such compression system is known as a lossy system. We can implement this encoding and decoding in the form of a program, or we can have a dedicated device for that. A device which performs encoding and decoding is known as a codec. Now let us discuss this each module in detail. First one is encoder. So first stage in the encoder is the mapper. This mapper module is designed to reduce the interpixel redundancy. The run length coding is an example of the technique which is used in this module. The operation performed by this mapper module is reversible. The second module is known as a quantizer, and it is designed to reduce the psychovisual redundancy. In this stage, the process which is performed is known as a quantization. In the first unit, we have seen the concept called sampling and quantization. The same task is performed here. So here, in order to reduce the psychovisual redundancy, the wide range of the intensity value is mapped to a single intensity value. That's why here there is a loss of information, and that's why the operation performed by this module is irreversible. The next module is known as a symbol coder, and it is used to reduce the coding redundancy. Generally, in the original system, we may have a fixed length coding. Okay, so generally, in order to represent our image, we use 8 bits per pixel, right? In this module, we apply the technique such as Huffman coding, and we will encode the image using variable length coding, and thereby reducing the coding redundancy. The operation performed by this module is also reversible. So the operation performed by mapper is reversible, the operation performed by coder is also reversible, but the operation performed in the quantizer stage is irreversible. That's why that process, the complementary process of the quantization, is not present in the decoding phase. In the decoding stage, we have two components, and the operations are performed in the reverse order. For the symbol coder, we have here the symbol decoder. As we have seen, the quantization results in irreversible information loss. We don't have the inverse quantizer block in the decoding stage, and for the mapper we have corresponding inverse mapper here. So this is the functional block diagram of general image compression system. So in this way, any image compression standard may have some of the blocks which are present in this general compression system, or will have all the blocks which are present here. Now let us discuss lossless versus lossy compression. As we have seen in the general compression system, only quantizer module is irreversible. That means if we don't include that module, we will get the lossless coding, and if we include that module, then there will be some information loss and we will have a lossy coding. So in lossless or reversible compression, the reconstructed image after decompression is identical to the original image. Okay, so there is no information loss, but generally we get low compression ratio in case of a lossless compression, and they are ideal for the applications where we cannot tolerate the information loss. Okay, so those applications are applications in the medical field, or means archival of the business document. So in such cases, we want the original image after the decompression. And in case of a lossy compression, the reconstructed image after decompression is degraded with respect to the original image. Okay, so here we eliminate multiple types of redundancy. So here we have a loss of information, but here we achieve a high compression ratio. Typically, it is used in multimedia applications, so where the loss of information is acceptable.